Hey everyone, I'm Nguyen-Tu, and this is Lab 4 of Physics 2211. The purpose of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. In this lab, I will be using Newton's second law and the momentum principle. Newton's second law is force equals mass times acceleration that tells us the acceleration of an object is directly related to how much force is applied to the object. The momentum principle tells us that in an isolated system, momentum is conserved for any interaction between two objects. Incorporating these two physics principles in my model with the velocity update formula, obtained by dividing both sides of the momentum formula by the mass of the object, I can predict the motion of my chosen object over time. Also in this lab, I'll be using the energy principle and the law of conservation of energy. The energy principle tells us that the energy of a system is the energy already in the system, known as heat and denoted as Q, plus the energy given to or removed from the system by its surroundings, known as work and denoted as W. The law of conservation of energy tells us that energy is neither created nor destroyed. Therefore, the change in energy of the system plus the change in energy of its surroundings should be equal to zero. Of note, the relevant energies and forces formulas used in this lab are shown, specifically kinetic energy, spring force, spring potential energy, and gravitational potential energy. To complete this lab, I'll be following 4 steps. First, I'll collect the coordinate positions of a mass as it swings in an arc while oscillating on a spring with tracker. Second, I'll transfer the collected data to a .csv file to plot the data through GlowScript. Third, I'll modify the provided GlowScript code to model the mass swinging in an arc while oscillating on the spring. Fourth, I'll compare the model predictions to the observed data. The main result of this lab is that the observed motion of the spring mass system had slight differences from the model predictions that indicate a loss of energy from the system to its surroundings, while the model predicted total energy to remain constant. Shown here is the observation video being analyzed with tracker. In my GlowScript model, the system is the mass, spring, and earth, the surroundings is nothing, and the system initial conditions are the mass of the mass being 0.402 kilograms, velocity is 0 meters per second, and time is 0 seconds. Modeling the system, I make 3 assumptions. 1. The only forces acting on the mass are the force of gravity from the earth and the force from the spring. 2. The mass of the spring is negligible. And 3. The mass only moves in the vertical and horizontal directions. Underlying these assumptions, I'm assuming air resistance and friction both have a negligible effect on the system. Shown on the right is the model of the spring mass system. The origin is colored yellow, the spring is colored cyan, the model of mass is colored blue, and the observation mass is colored red. The code detailing the colors of each component is shown on the left. Shown here is the GlowScript VPython code where the system properties and initial conditions are defined. Lines 48 to 58 scans this .csv observation data to be plotted in the position time graph shown earlier. Following assumption 3, the initial position of the mass has no z coordinate with an x component of negative 0.116 and a y component of negative 0.64. Of note, delta t is set to 1 divided by 210 to allow for 20 model predictions before each observation is plotted in the graphs. Shown here are the interaction constants and the initial values of the spring and system energy. Of note, the spring constant was given but calculated by solving for k in the period of oscillation formula to get that k is equal to 4 times pi squared times the mass divided by the period of oscillation squared. Also, the relaxed length of the spring was given but found by solving for L0 at the force equilibrium point where the force of gravity is perfectly balanced out by the force of the spring. Here's the calculation loop for the model that stores the initial values of the energies each iteration before calculating the net force by summing the calculations of the force of gravity and the spring force. The momentum principle is applied to calculate the object's new velocity and position with the velocity update formula and the position update formula respectively. The spring's values are then updated. Here's the rest of the calculation loop where the new energy values are calculated, the change in energy is calculated, and the values of the model and video observations are plotted into the graphs. Time is updated at the end before the next loop iteration begins. Now for the discussion part of this lab. For my model system, is the energy principle satisfied? According to the change in energy over time graph, the energy principle is satisfied because the total energy of the system is conserved as indicated by the orange line representing the change in total energy remaining relatively constant at 0 as a straight line. Since the model says energy is constant, we should see the mass traveling the same distance over the same amount of time as shown by the model's graph in blue. That being said, plotting the positions of the observed mass over time in red shows that the same distance was not covered over the same amount of time, most obvious in the y position time graph, which indicates that some energy left the system to its surroundings. The period of oscillation can be found by determining the time in between two crests or two troughs. The average period of oscillation for the observed x position of the mass is calculated on the bottom left by averaging the times in between the crests of the x position time graph. Similarly, the average period of oscillation for the observed y position of the mass is calculated on the bottom right by averaging the times in between the troughs of the y position time graph. Since the period of oscillation is used to calculate the spring constant, the difference of 0.26 seconds means that I could calculate an incorrect spring constant if I only used one or the other, which would result in an incorrect spring force and spring potential energy calculations in my model. This difference in oscillation can be caused by dissipated forces like the air resistance and friction mentioned earlier, or issues with the tracking of the mass in the video. In this lab, there are two main possible sources of error. First is that, unlike assumed, the dissipated forces of air resistance and friction are likely not negligible since the observation has evidence that energy is not constant. The second is that the mass did not purely move in the horizontal and vertical directions, which could also explain the evidence that energy is not constant.